Alright, so we're going to take a bit of a musical trip around the world in order to explore about sound. So we're going to look at these instruments from different cultures, because all people have a love of music and they find amazing ways to express their creativity through manipulating sound. And so as we study the physics of sound, we're going to use these examples of different musical instruments to demonstrate different parts of the physics. So to start with, this instrument is called a balafon. The balafon is from West Africa. And you can see that it has these different keys . And maybe you would like to make a note about the length of the key, the size of each key, in relationship to the pitch of the note that it produces. The big keys versus the small keys, the high notes versus the low notes. Similarly, if we look underneath the balafon, we're going to see that it has a series of gourds hanging underneath it. And these act as resonators. They kind of help this sound project more. But notice that there is a relationship between the size of the gourd and the pitch of the note. So what is sound anyway? Well, in this case, sound is being produced by a percussion instrument. It happens to be a melodic percussion instrument. It's percussion because it's played by hitting it, and it's melodic because it has different note values. But the sound itself, whether it's percussion, strings, voice, horns, or some industrial sound like a car or a machine, or some natural sound like waves or wind or birds, it always involves producing a vibration that travels through the air. So when I hit this key, I cause it to vibrate back and forth very rapidly. Now this one is vibrating at a somewhat different speed, and that's why we can tell the difference between the notes, is the vibration speed is different between each note. And this vibration travels through the air, vibrating the air molecules back and forth until it strikes our eardrum, and then our brain converts that to the perception of sound. Alright, so this instrument is called a bodhrán, and it's from Ireland. And what I really want to show you on this big drum, it's one of a family of frame drums, but what I really want to look at is vibration, and how the vibration is what's creating the sound. So when I hit this drum, I make vibrations, right? If I hit the edge, it's vibrating faster than it is if I hit it in the middle. And you can tell by the pitch. We're going to talk more about that in a minute. But to really show the vibration, I'm going to put this rice on here. And then if I hit the drum, you can see the vibration move that rice around. And what I want you to notice is the rice doesn't stop bouncing right away. It keeps going. And every time it hits the drum head, it too makes a little bit of a sound. And so we get that buzzing sensation. But the whole point is vibration. Vibration equals sound. Okay, before we move on to the next segment, there is one thing I should have mentioned about sound, and that is when the vibration occurs in the drumhead, that vibrates the air molecules next to it, which vibrates the air molecules next to them. And the next set of air molecules vibrates until finally the vibrations reach our eardrum. Now, if there's no air molecules between the drumhead and the eardrum, then those vibrations cannot be transferred to your ear. So the vibration of the drumhead in space would still happen. This drumhead would still be vibrating up and down, but it would not move any air molecules, and so the air would not be able to transfer the sound to your ear. In space, there is no air. Because of that, there is no sound. The vibration can't make it without having the air to transfer it. At any rate, we're going to now look at this Native American flute. So this is a flute from North America, made by native peoples. There's a great story about how the woodpecker gifted this instrument to native people. And as you can see, it has these holes in it that change the notes, right? If we cover all of them, we get a low note. If we don't cover any of them, we get a high note. And so now we want to start thinking not only about vibration, but about the sound waves. So when the person blows through the flute, the vibration creates a wave. And it might be a long wave. In the case of the low note, if these are all covered, basically the tube goes all the way from here to the end. That's for a low note. It's a very long wave that's vibrating. On the other hand, if all these are open, all of a sudden my tube is really only this long because the air is escaping from this hole. And that means that we have a short wave. And this leads us to the concept of wavelength. And that's part of how we measure different sounds, is by their wavelengths. So a wavelength is the distance between one peak and the next peak. If you think about it, you could also define it as the distance between one trough and the next trough. Sometimes these peaks are also called crests. It's the top of the wave. That's the wavelength. And we measure that just like we would measure the distance from anything, with centimeters and meters and inches and feet, or very small or very large measurements also. Now in physics, we use a Greek letter called lambda. L-A-M-B-D-A, lambda. It's equivalent to our letter L, and a capital lambda looks just like the letter L, but this is the lowercase lambda which we use to represent, it's the symbol for wavelength in physics. So, how big are these waves? What are the wavelengths that humans are actually able to hear? Well, the highest pitch notes that people can hear, very short lambda, very short wavelength, those are about 1.5 centimeters long, about half an inch, maybe the width of my finger. That's how close the peaks are to one another for the highest pitch note that most humans are able to hear. Of course, as you get older, you start to lose those higher pitches from your hearing. So you want to protect your hearing when you're younger so you can keep hearing all those beautiful sounds out there. The lowest pitch that humans can hear, the longest wave, is more than 50 feet long. It's 17 meters. So this also tells us something about listening to music in a concert setting. Because these small waves in the high pitches are so short, they are smaller than a human head. That means that if you're behind somebody, their head is going to absorb the high pitches. But the big notes, the low notes with these really long wavelengths, can go right around them. And so you hear the low notes just fine. So if you really want to hear that guitar solo, you want to make sure your head is up above the crowd. All right. Well, these drums are from Latin America. I think they really grew out of an African drum. This is an original one over here, the ashiko. And these bigger ones are called congas. And then these small ones are bongos. So widely used in Cuban music as well as other types. But what I want to point out is, as a drummer, if you want to get different notes, you often get drums of different sizes. And if you look closely, the drum head here is bigger than the drum head here. This is the smallest one. And as a result, the small one vibrates quickly, and it's going to have a high pitch compared to the biggest one that vibrates more slowly. This is also influenced by the size of the body of the drum. As you can see, the higher pitched bongos are much smaller than the lower pitched congas. So for drummers to get different notes, one of the ways is to have more than one drum with different sized drum heads and different shaped bodies. All right, and this is a modern American drum. It's called a rototom because it rotates and it's a tom-tom. So, one way we can change the pitch of a drum is by tightening or loosening this drum head. If we tighten it, and that's what these bolts are for, if we tighten it, it makes it higher, and if we loosen it, it makes it lower. And once again, that's all because it changes how fast the drum head vibrates. If it's tighter, it vibrates more quickly, and if it's looser, it vibrates more slowly, so it has a lower pitch when it's looser. But what they've done with the rototom is allow us to rotate this drum and loosen the drum head so it makes a lower pitch, vibrating more slowly or more quickly. As I tighten or loosen that drum head. And so these pitches are based on waves, but they're also based on vibration. It's both at the same time. So these vibrations move in waves is one way to think about it. So the tighter it is, the faster the vibration, and we refer to the speed of the vibration as the frequency. Frequency, how fast it vibrates, how fast that wave shakes back and forth or up and down. So here's one way to look at it. Frequency we represent with a small letter f. If it has a low pitch, it's going to vibrate slowly. It's going to have a slow frequency, which means it has a very long wavelength. It would look something like this. Long waves. Lambda wavelength. On the other hand, if it has a high pitch, it's going to vibrate very quickly. It has a fast frequency, and along with a fast frequency, it has a short wavelength, short lambda. So it would look more like this. And can you see that this one is vibrating much more quickly than this one is? But the distance between waves is much shorter than here. So if it has a slow frequency, it has a long wavelength. If it has a fast frequency, it has a short wavelength. So these two vary together. They're locked together. When you change one, you're going to change the other. Alright, this instrument is called the Barombao, and it's from Brazil. Here's how you spell Barombao. And so the Barombao, we think, is perhaps the oldest string instrument in the world, and it's found in different variations in many cultures. It's basically like a bow and an arrow. And we think that maybe hunters first invented this by tapping on their bowstring with their arrows. And then it grew into this musical instrument, the musical bow, the Brazilian version like this one, the Barombao. And the way we change its pitch, we have this vibrating string, and I make it shorter by pressing on it with this coin. The gourd down here acts as a resonator to amplify the sound. So once again, I'm changing the pitch. By changing the frequency of vibration, I make the vibration faster by shortening the string. I make it slower by allowing the full string to vibrate. And traditionally you include this shaker in this hand at the same time. Now this instrument is best known for its use in a martial art form from Brazil called capoeira, where as the people practice, they also play the Barombao. And so sometimes they call it a dance, even though it's a martial art. Now, as far as the science goes, we measure the frequency with a unit called hertz, named after a scientist. And the symbol for hertz is Hz. So this is how fast the waves are vibrating. It's also known as cycles per second. It's how many vibrations in 1 second. So 1 hertz would be 1 vibration per second. For humans, we can hear from 20 hertz at the lowest, because it's the slowest, it's the lowest pitch. We can hear all the way up to 20,000 hertz, also known as 20 kilohertz. So if you're ever shopping for speakers or a sound system for your TV or something, you want something that goes from 20 to 20, 20 to 20K, 20 to 20,000, because that's the range of human hearing. Below that, we can't hear it. We call it infrasound. And above it, we can't hear it either. We call it ultrasound. So bats will use ultrasound. Elephants will use infrasound. And actually, if you have a subwoofer, you might take it below the realm of human hearing because you can feel the vibration in your body, even if your ear can't detect that infrasound. The other cool thing about capoeira and the Barombao is that back in the days of the slave trade, the slaves developed this martial art using the musical bow. And of course, the slave owners would not be very happy about their slaves practicing a martial art because it could lead to a revolt, which it did. But the slaves were so smart because the person playing the musical bow, if he saw the plantation owner or the foreman coming, he would change the rhythm, giving a signal to the slaves to just do a happy dance instead of practicing their kicks and their flips. So you can find places to study capoeira yourself today, mostly in big cities, but Well, this instrument is called a talking drum, and it's from Africa. And the best players can really even tell stories and jokes using this drum because it's thought to mimic human language by changing the pitch of the notes. It talks, at least if you're an expert. Now listen to the difference between a quiet note and a loud note. So they have the same pitch, the same frequency, and the same wavelength. They're vibrating bigger or smaller though. And we call this the amplitude of the note, which is represented by the letter A for amplitude. And a quiet note is going to have a very small amplitude, small waves, whereas a large note, a loud note, is going to have these big waves. Big amplitude from top to bottom, small amplitude from top to bottom, quiet and loud. Now, amplitude, notice, is the wave height instead of the wave length. That's the pitch. If I change the distance between these waves, if I squeeze them together, I get a higher note. If I stretch them out, I get a lower note. But now we're talking about how tall the waves are. Louder is going to be these taller waves. All right, so these drums are called tabla, and they're from India. And the Indian tabla are amazing drums because you can get so many sounds out of just these two little drums. And partly it's because of the way the drum heads are made, and partly it's because you use different parts of your hands and fingers to get different sounds. If we look closely at this drum head, you'll see that it has an outer rim, a middle section, and then this whole center black area. And each of those is built differently and vibrates differently to make different notes. So the basic drum head is here in the middle, in between the edge and the center is what I'm talking about, the middle here. This right here. Now in the center of the drum, we've added this black material. It's a paste made of flour and iron filings and glue that gives it this ringing tone, kind of like a bell. And on the outside edge, we have a double thickness of the drum head. So this is got a little different sound depending on where you hit the drum. And with the bigger drum, we modify its tone by pressing with the heel of the hand or releasing. So if I want a higher note, I press on it. It kind of makes the drum head smaller, shorter vibrations, higher pitch. But if I release, the whole drum head is vibrating now, so it's vibrating more slowly and a lower pitch. So I can modify the pitch of the drum by pressing with the heel of my hand. The other thing we can do with these drums is play either open or closed notes. And what I mean by that is whether we allow the note to ring out or not. These would be open notes. A closed note, we just leave the finger there for just a fraction of a second to prevent it from ringing. So here's a phrase called Kitatakaterekita din. all the notes have names in Indian music. And so this particular one is 8 closed notes and 1 open note. Kidda-taka-tada-kita-din. 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 Kind of a drum roll there. All right, so let's talk about pitch a little bit more. So with the tabla, we're modifying the pitch, especially of the low drum, and we actually tune the high drum to a perfect note that matches the other instruments. But I want you to remember that if it's a low pitch, it vibrates slowly. F is for frequency. That's how fast it's vibrating. Frequency of vibration. It has a slow frequency vibration. We measure this in hertz. So this is going to be a small number. Like the lower limit of human hearing, the lowest pitch we can hear is 20 hertz. Over here for the high pitch, it's going to vibrate fast. It has a fast frequency. And that means we have a really big number for hertz. Like for human hearing, it's 20,000 hertz. Compare that to the 20 of our lowest pitch that we can hear, from 20 to 20,000. Now, the frequency of vibration is related to the wavelength, as shown by this letter lambda, Greek letter lambda. And this is going to be a long lambda, and this is going to be a short lambda. So the low pitches, they vibrate like this. They have a long distance between one peak and another, from crest to crest. This way is pretty long compared to this one. They have a short lambda over here. So they vibrate much faster, and the vibrations are shorter. The waves are shorter. The wavelength is shorter. Wavelength is longer over here. So if you look closely, you'll see that we have what we call an inverse relationship between the frequency, measured in hertz, and the wavelength. They're opposite from one another. The bigger the frequency, measured in hertz, the bigger this number, the smaller this number. That means they're inverse from one another. As this one gets bigger, this gets smaller at the same time. This is just the opposite. Here we have a really small number, but a big wavelength. So they vary in inverse proportion to one another. They're opposite. All right, next we have this musical toy from modern America, and these are called boom whackers. So these boom whackers are tuned percussion tubes. This one is tuned to the note D. And you play them. This is one way to play them. So they're basically tubes. I'm setting up a vibration, and then it creates this note. And the first thing I'd like you to do is predict which of these will have the highest and the lowest notes. And we can just refer to them by their length. Which is going to have the highest note? Which is going to have the lowest note? What do you think? Let's put them in order here. I'm putting them in order by length. Right? And hopefully you said that the lowest note is going to be the longest one because it's making a bigger wave. Not a taller wave, a longer wave. Remember, wavelength. Right? So the longer it is, the lower it is, the shorter it is, the higher it is. So again, it's that inverse relationship where it's got a big wave and a slow frequency, or a very fast vibration but a very short wave. Now the next thing I want you to notice is that the notes are actually labeled on here. C, D, E, G, A, C. Well, these are both C. How can that be if they're different notes? We say these are an octave apart. They're 8 notes apart, octave. Now, check this out. Look at the length of them compared to one another. Let's see, if I set that right there, and I mark this spot, how tall? Look at that. It's almost exactly twice as long, isn't it? The big one is twice as long as the short one, right? And that's what defines an octave, is that the wavelength is twice or half the size, depending if you're getting the bigger one or the smaller one. The wavelength doubles to increase excuse me, that's backwards. The wavelength doubles to decrease the octave. So this one has a wavelength that's half of that one. This is double of this one. But at the same time we change wavelength, we're also changing frequency, remember? So this one vibrates twice as fast as this one, exactly. And that's what makes them an octave apart, is that this one has a vibration half of that one. So you can always figure out how to go up or down an octave if you're given a number of hertz. Let's just say 1,000 hertz. If this one's 1,000, and this is exactly an octave below that, we divide by 2. So this would be 500 hertz. On the other hand, let's say this one was 10,000 hertz. To find the octave above that, you double it. So this would be 20,000 hertz. Always double or divide by 2, halve, to find the octave. Okay, this instrument from Ireland is called a hammer dulcimer because you play it with these little hammers, these little sticks. And as you can see, it's a string instrument, and like any string instrument, we have to tune it by adjusting how much tension is on the strings using these pegs over here. So when I play this instrument, I want you to notice the length of the strings changes as we go from the bottom to the top. Here they're a much longer string, and here it's a much shorter string, right? So describe the relationship between the string length and the pitch. So what happens? To describe the relationship, what you need to do is say something like, the longer strings have such and such a pitch. Or you could say, the shorter the string, the pitch. Describe the relationship between them. Now I want you to include wavelength and frequency as part of your description also. So think about the wave that is being produced by these longer strings compared to the wave produced by the short strings. Which one's going to make a bigger wave? Which is going to make a shorter wave? Which is going to have a faster? Which is going to have a lower frequency? Which one vibrates faster, has more hertz, or vibrates slower with less hertz? Include that in your description. So the other thing that's kind of cool about this instrument, well, it's really what's cool about an app here that allows me to tune it. So let's see, here's my tuning app. Of course, there's ads in it. But I can take my tuning wrench and my app and this little cheat sheet that shows me what note should be what, right? Let's see, this first one should be an A. Let's see how close this says. Pretty close. You can tell by that red that it's a little below A. Now what I really want you to notice is that it gives the hertz. It gives the frequency here in hertz. So 217 hertz should probably be 220 because that shows me it's a little flat. So I need to take my wrench and tighten this guy up just a little bit. That's better. Pretty close to 220. Now, if this is an A, and up here is another A, they're an octave apart. It's the same note, the same pitch, one octave apart. And if this one was 220, what's that one going to be? Let's see, shorter string, it must be a higher octave. Remember, to change octaves we have to double, so this one should be at 440. If this one was 220, then the next A up should be twice that at 440. Ooh, that one's pretty close. Again, I'm looking right here at the number for hertz, the frequency of vibration. It's vibrating 440 times in 1 second to make that sound. 440 times a second. Down here, it's vibrating only half of that, 220 times a second. They are an octave apart because one is twice the other. All right, so here we have the marimba, which is really from a variety of places around the world. You can tell this is kind of the modern version of the balafon that we started with wooden keys that you strike. This particular marimba is 2.5 octaves, and it's from Brazil, but they're also very common in parts of Central America, like Guatemala, and they're used in modern European and American orchestras as well. So the marimba has these keys of different sizes, right? And this is kind of quiz time, and I want you to predict which key size has the highest and lowest note. Once again, what's the relationship between the size of the key and the note? Okay? Similarly, underneath we have these resonators. Now with the balafon, the resonators were gourds. These are actually cardboard tubes underneath here, and notice the length of the tube changes in a regular pattern that matches the length of the key. And so I want you to describe the relationship between the length of the resonator and the pitch. Okay, next. Today, a modern orchestra, and it wasn't always this way, they've changed since the time of like Beethoven and stuff. Today, a modern orchestra, I don't know if you can see that or not, they tune to this note, A 440. A equals 440. And of course that's in hertz, or vibrations per second, cycles per second. A440. That's the modern tuning for an orchestra. So here's an A, and the next A on this marimba is up here. They are one octave apart. So if this A is 440, what is this A? You tell me. How many hertz? How many vibrations per second does that high A have compared to this middle A? Now my marimba doesn't quite go down to a third octave, so it's missing that lower A, but what would it be? How many hertz would it have if it's exactly one octave lower than this A440? If this one's 440, tell me an A one octave higher and an A one octave lower, our imaginary A down here. How many hertz? All right, so now we've got a thoroughly modern instrument, the electronic drum kit. And what I want you to think about is how it makes these different sounds. How does it mimic a hi-hat, or a tom-tom, or a bass drum, or a cymbal, a snare drum? How does it do it? Because if I turn off the power to this device, the only sounds we get are these little thuds, right? So nothing's happening until we turn on the power. Now, inside of each of these trigger pads or detectors, I don't know if you can see them inside this one here, there's these detectors that pick up the vibration from the impact of my stick with the trigger pad. And then the trigger pad sends an electric signal to the controller. And each pad has its own wire, since it's sending its own signal to this controller. But the controller still isn't making the sound yet. To get the sound, the controller sends an electronic signal that includes all of these combined to a speaker. And so here's a speaker behind me. And if you've ever looked at a speaker, you can see when it's running, it moves back and forth. And that's the vibration we're seeing. It's vibrating the air molecules, and those air molecules pass the vibration to our ears. Now, if the speaker vibrates a lot, that's going to make a really loud sound. And that's how people can blow out their speakers. If it vibrates too much, it can actually tear the speaker apart, because they're often made of a paper that's vibrating. On the other hand, if it vibrates just a little bit, it's a quiet sound. And of course, if it vibrates quickly, it's making a high-pitched sound, and if it vibrates slowly, it's making a low-pitched sound. So by sending a signal that combines the speed of the vibration, the frequency in hertz, combines it with different aspects of sound, the tone of the instrument, and combines it with the amplitude, the volume, we get this whole different mix of sounds. And of course, with the controller, I can change those sounds to be something, how about a marimba? It's all in what the controller tells the speaker to do. I can also get kind of some African sounds. So, I want to thank you for joining me in this exploration of sound around the world and these different instruments, and hopefully we're able to apply those ideas to the physics of sound.